So geometrically, we all know vectors is something we normally picture as an arrow, like these arrows you have here, and normally you give a name to the point in the initial point of this arrow and the point at the final point of this arrow. The other way you normally denote vectors is with the little letters, and put a little arrow above it, and the identity between these two normally expressed like this. The AB vector, so the vector which originates from a point A and finishes with the point B with the arrow above, is the same as like little a with the arrow above. In the notes which you printed, you also, probably if you read them already, you saw that actually notes uses a third notation for vectors, a boldface little letter printed in the boldface. It's here. Unfortunately, with this kind of resolution on the screen, you can't really distinguish boldface very well, especially for the people in the back row. So that's why I stick with the arrow, with the little letters with the arrow above it. I'll try to stick with those. But the lecture notes, I said it already, they use the different convention. They use the boldface letters. And in fact, most of the tutors here probably, in order to uphold this notation with the boldface, we also are unable to produce the boldface on the blackboard when you present their handwritten solutions to you. They will probably do it like this. They will put the letter and they put the line under the letter. I'm not sure if I can produce it here. I'll try. They will use a notation like this: little letter with the underscore or line under the letter. Normally, this kind of notation just says that the letter in the boldface. It is because when you have a chalk or a pen for the whiteboard, you can't make a boldface, so they use this convention. So all of this you should be aware of to make your understanding of what's written is easier. But like I said, I'll try to stick with the arrow in my presentations like this. But sometimes I may forget about that. Now, geometrically, there are a few things we can do with vectors, and all of them presented on this slide. I'll just give you a brief brief review of these things. First, the identification of vectors. With vectors, we make this convention that two vectors are equal when they can be matched with each other by the parallel transition. That's what is said here. These two vectors, the blue one and the red one, in fact, from algebraic point of view, two identical vectors, because they matched by the parallel transition. Now, the other thing which you probably know about what we do with vectors, it's a scalar multiplication of vectors. Normally you write it like this. You write it like this. Sometimes you may omit the dot in between and shorten down to, oops, not to this, down to this. That's how we write scalar multiplication of vectors. And geometrically, this is basically the stretching or shrinking of vectors, and that's what I explained on this diagram. If I have a vector, A, which originates from this black point, and the blue vector which ends here, when you scale this vector, lambda times A, and your lambda is bigger than 1, you end up with the stretching of the vector in the same direction. If you scale this vector with lambda which is less than -1, you end up with the stretching. That's this vector. Or it's also stretching, but it's in the opposite direction. Now, when you scale your vector with the coefficients, with scalars, which are, for instance, like this, which is between 0 and 1, this is shrinking, and that's the result of this shrinking. You see my vector gets shorter, but it kept the direction. Now, if you multiply your vector with the scalar negative, but still in absolute value less than 1, this is again shrinking. This is this red vector, but the direction went into the opposite. That's effectively what happens when you multiply the vector with the scalars. I didn't mention this here, but when I say scalars, in this context, of course, we talk about real numbers. So remember, that's a good correspondence between the algebraic operation and the geometric operations with vectors. When we scale the vectors, effectively, this is scaling, this is shrinking or stretching, and optionally reversing the direction. Right. Vectors, you know it probably, sometimes they're like when people talk about the vector quantities, they say vector quantity is sort of like carries two things at once. They carry the magnitude and they carry the direction, right? But there is one vector which doesn't have a direction. It has only a magnitude. Who knows this vector? Thank you very much. It's a 0. Every vector besides 0, they have two parts of it, the magnitude or the length, and if you don't know it, the length of the vector we denote with the two vertical bars, so sometimes it's also called the absolute value of the vector. So if you heard the term absolute value of the vector, that's undoubtedly refers to the length of that vector or the magnitude of that vector, and there is also the direction of the vector, which we don't have a special notation for, but some of you may know that you can do it by scaling. In fact, you can always extract the direction only from a vector by doing something like this, by multiplying your vector with the inverse length of that vector. If you do this kind of operation with your vector, and we know this is basically stretching or shrinking, what happens with the vector if I shrink it or stretch it by the inverse of its length? I end up with a vector which keeps the direction. Pay attention, the coefficient here is positive, so it keeps the direction, but the length of this combined vector will be 1. So basically we just rid of the magnitude information from that vector, but we kept the direction information of that vector. So every vector has these two components, the magnitude, or aka absolute value or length, and the direction, which is given by this unital vector. Unital, if you haven't heard this term before, it refers to the vector with the length 1. Every vector is such, beside very special distinguished vector, which is a 0 vector, for which you cannot extract the direction, because if you try to do this algebraically, like this, if you try to extract the direction from a 0 vector, you will hit unavoidable obstacle because you cannot divide by 0. The length of the 0 vector is 0. So the 0 vector is the one which is just a point. It's here on this diagram. Now, addition of the vectors. Normally we can do additions two different ways. One of them called the Parallelogram Rule. The other one is called, if I'm not mistaken, triangle. Oops. Oh, it's gone. Triangle Rule. And you do it like this. If you have two blue vectors like this, like here, you get your vector A and you have your vector B, you just build up the parallelogram based on these two vectors, and you call the diagonal of this parallelogram, which originates from the same origin as your two given vectors, from the same origin, you call them the sum. Triangle rule looks very similar, but you build up, instead of the parallelogram, you build a triangle. So here's your A vector, here's your B vector, and the sum will be the vector which goes from the origin of the first vector towards the endpoint of the last vector. A little modification, if you do a little modification to this addition rules with the help of the scaling, you will realize actually that when you subtract two vectors, A and B, the difference will look like this. The difference of two vectors B and A, it's the vector which originates from the tip of the second term in your difference and ends at the tip of the first term in your difference, given that the original vectors, they come from a common origin, from the common origin.